Okay. So I was looking at, we recently came up with um, how to select stuff like for if you're doing an unstructured mesh, right, and you have that partitioned across multiple process ranks, that odds are, and you're maintaining a global numbering scheme, that you're going to have many different selections kind of randomly selected for each rank. So it's kind of looking in the best way to do that. And there's the two options, right? There's the hyperslab selection or element selection or point selection, whatever you want to call it. And Quincy, remember this? We did the Moab was doing had this same type of issue, right? Because they were doing the same thing, and we were helping them trying to figure out the best way to do that. And so what I did is just write a simple program to just investigate the performance comparing the hyperslab selection to point selection, and when does one outshine the other, I guess. So yeah, as I mentioned, this is kind of typical for unstructured meshes. So I did three cases. So I did one case, this is the worst case possible. This is extreme case where you have one element per selection. So you assign one hyperslab per element and or one, and then you also do one point selection per element. So that's the extreme case. And how I arranged it was each rank, so each rank's a different color. So each rank will have part of this, and then we'll select each element, and then I will shuffle those so they're kind of random, which my understanding is not as that randomness is going to be de-randomized when it does point selection because it's MPI requires them to be in order. So it's going to order those. So in that case, the point selection is going to be contiguous in memory, no matter if it's randomized or not. Whereas the hyperslab will not be random, will not be contiguous. Odds are. The second case, I just did a typical one where you just do the whole hyperslab per rank. So one rank just does a whole selection. And I did the same thing where I specified the points that would cover the same hyperslab selection.
Well,
The third, the third one I did was multiple selections where I specify like a width, so a certain number of contiguous elements. And for this case, I did four contiguous elements, which would be typical maybe if you're doing like a finite element where you have a tetrahedra or something, you'd have four for each element, you'd have four um, nodes assigned to that. I also looked at a width of 256 elements, and you'll see the next slide. So this is kind of so each rank will be it will be split over this. All this is a 1D array too. I'm going to say so it will skip. So rank one will do the green here, and then it'll do all the others. Ranks will be assigned to different part of that array, and then rank two will be assigned the next, and then I shuffle those so they're not in order. So they'll be all over the place where the offsets are, where they begin for both the hyperslab and the point selection. So in this case, it should never be contiguous, even if they reorder it in the file itself. The memory won't get mapped to the contiguous part in the file. So here I have the total times. This is the total time for the program I just didn't time the writing. I timed the completion from opening the file and then closing it, writing the data. So the first case is the hyperslab, and I compared um, the independent and collective. And so the first case is the hyperslabs, you're using hyperslab selection with independent. Next is hyperslab with collective. The other one is you're doing point selection with independent and collective. So you can see quite the difference between the hyperslab. Oh, and this was run on Frontier. The array was over 1 billion elements long, but that translated, it was 2,048 ranks. So that translated roughly about 65K elements per rank. So it's not large on a per rank scale. And then this is so obviously point selection did much better than hyperslab selection. And this is an extreme case, right? Where you have one hyperslab per element definition, and you just keep appending and appending hyperslab. The next case is where you just do the whole hyperslab, and you can kind of see that, of course, it's just one writing of the hyperslab, but same with the points range, and they're about equivalent, which you kind of expect. And then the next case is the one I just mentioned, where you kind of have a number of contiguous number of elements on each rank, and then you kind of shuffle them. So the first case I just did those. So this was a case of 4 contiguous per selection. So the first case is hyperslab independent, then hyperslab collective. I can see it performs much better collective. The next is elements point selection, and then independent and point selection collective. So still, and all this is right at the same data. So it's starting to approach the hyperslab contiguous in one right, but still it beats hyperslab selection. Now, when you get the case where you have a wider, it's starting to approach the, so this is a block size of 256 instead of the 4 here. And you can see that pretty much collective independent for, at this scale, pretty much didn't matter. And they all perform roughly starting to approach what you would just get with the whole set hyperslab. Now, Jordan mentioned that if I were to do extremes and do lower number ranks, so you have 500 million roughly per rank, Jordan suspects, and I'm going to look into it, that since point selections using linked list, that the cost of creating that linked list and destroying it will probably be, when you get to that scale per rank, will probably really hurt performance compared to hyperslab. So it kind of, I guess it depends on what your situation is, of course. Where I want to see if first that's the case, it probably is, and see how much hyperslab is beneficial and where that. So if you have a lot of ranks or a lot of elements per rank, it might be still beneficial to use hyperslab. But in terms of this, it seems the point selection does. And I had the impression, at least from what we did a long time ago, that point selection was hardly ever as good as hyperslab, but it appears that I might have been wrong. So it's good to always go back and verify your assumptions that were made a long time ago and whether they're still true. But so that's just a little study that I was working on. But I plan, as I said, to do it with a lower number of ranks to see if it really matters. Because I mean, maybe it doesn't matter because it's really CPU intensive, and maybe the computers are so fast that it doesn't matter as much as it did 10 years ago. But it'd be nice to know for sure. So, any questions about that study? I never decided, I don't know what if how Moab decided to change their data structure. But they were using the point selection. It was pretty slow back. That was a long time ago though.
And they needed the point selection because the hyperslabs wouldn't have given them the same ordering on the way out to the file. Or it was just stored in memory very discontiguously in many locations in memory. That was impossible. I don't recall with.
Yeah.
I mean, if point selections turn out to be a win in some of these cases, we can optimize the memory more, not perfectly, but more, by every time you append internally in the data structures, every time you append a new point, you could see, hey, is this adjacent to the previous point, and make a span that grows, because I think you just increment a number inside that description of the sequence of points. I don't know what kind of special cases that will require from the applications. We can detect it and implement it, but I don't know if enough applications would use it to justify the effort.
I know this is still a problem though, because I mean, we were working with some people that had exactly this. They were doing unstructured meshes that was petitioned, and they were trying to figure out the best way to. They're using point selection. So
Yeah.
I know this is still a problem, at least with unstructured type meshes.
Yeah, well, to win, at least for that one optimization, you would have to have points in your data space be contiguous, right? So you'd be appending in the row-oriented manner, and also having those points be stored in memory contiguously, so that you could, otherwise you have to have a separate pointer for each location, even though the locations were in the data space contiguous.
Yeah, I mean, Jordan was kind of, I mean, obviously, I don't know if it matters. Well, this is not a very good case because it does reordering it, but this case is still kind of, it's it's shuffled in memory. So
Mhm.
I think Jordan was mentioning that there would be better options in doing a linked list because
Mhm.
allocating the linked list and then deallocating it, it thinks that the H5D create's going to take a long time. Same with H5D close, because it's got to deallocate all those element by element. And when you have 500, million elements to do that, he thinks that's what's going to cause the slowdown, not necessarily randomized where it's mapping the memory from to the file space.
Well, we store those nodes in the link for the linked list in a free list. So you will pay some penalty for malloc calls the first time through, but if you do more than one point selection for your application, you will dramatically drop the cost for allocating just this one piece of the algorithm, right? Allocating the nodes on subsequent point selection operations. So that may have diminishing returns, is kind of what I'm saying.
I see. Yeah. Yeah. That's why I really want to run larger number of elements per rank to see if it really, I mean, what the impact is.
Yeah, yeah. I think if you were actually able to find good, valid use cases and applications for this is contiguous in the data space and in memory, then we could consider that optimization I was thinking of. Otherwise, if they're bouncing all around in memory or in the data space, it's pretty difficult to make a smaller data structure than just a linked list of, well, here you go.
I think they're mostly in order. Well, I don't know how it is. I'd have to do like a mesh and then partition it and see how it maps out. But I don't, it probably won't be in order in memory or well, in memory, it'd probably be in order, but then it won't map in order in the file.
Mhm, mhm, mhm.
But, yeah.
Suppose we could start an optimization that was like blocks of descriptions and link those blocks of point descriptions together. The tuple of coordinate and pointer in memory, and make that be a block of tuples like that you allocated instead of, individual rows. You'd have an aggregate cost for here's a block of 128 of those or something. Yeah, a little bit wasteful perhaps if you had a one element point selection, obviously, right? Uh,
Mhm.
but really good, or much better at least, if you have 5 million.
Yeah, and Jordan maybe mentioned that your combined Hyperslab, does that have optimizations for, I guess, would that handle better the one, well, I don't know, this is kind of extreme, but maybe this case where you have just the four hyperslabs or four contiguous, but still in the
And
hyperslab?
if they're contiguous in data space,
Hmm.
then it will join them together as one block that describes that region. Yeah.
Okay, but it has to be contiguous.
Yeah,
'Cause
otherwise I gotta remember what the elements are. And they're different, and you don't get any advantage in joining them together necessarily. It's just, I could think of
but
small optimizations, but not big ones.
But how would that be different than just a pending one that's contiguous? It would be, you wouldn't see any difference, right? Between using the combined hyperslab and then just creating another, just a pending hyperslabs that are contiguous in memory.
Right, yeah, if you create it contiguously versus appending to build up to a contiguous region, you're gonna probably do worse in the building it up version, the appending version,
Mhm.
because you just have more overhead to cycle through. Oh, yep, we added another element, and end up with the same result.
Oh, I see. Okay.
They should, by the time you get to IO, they'll look identical, but just the initial overhead for building the data structure probably is higher in the append case.
Okay. Yeah, that was another case I was going to look into. Of course, I did in Fortran, so I didn't have the combined hyperslab. I didn't get that wrapper done, so I don't know. I'll have to do that if I decide to, or go to C, I guess.
Yeah, well, you don't necessarily need the combined one. You could use the select or operator on an existing hyperslab.
Oh, that's be the same.
Yeah, they'll
Okay.
just include new elements in the existing selection,
Mm-hmm.
and it's supposed to optimize for you. Yeah.
Okay. Yeah, I really want to see what the point selection looks like at larger number of element counts, the millions.
I
Let's
think
see.
it'll be, but he's currently not so awesome, but I can, like I say, think about how to make it better.
Mhm.
Especially, if you're presenting all the elements in one IO call, select point, or whatever we called it, element. And you tell it, hey, there's 5 million of these guys here. Well, then the algorithm can say, well, we can allocate a 5 million element tuple block and use that. If you just keep going or, and adding onto the end of the existing one, it's impossible to know how many you're going to add. And then harder to do the aggregation algorithm. But anyway, yeah.
Yeah, you could give it a hint if you knew how many points you were going to end up.
Yeah, well, if you present them all at once, right? If you tell
Mhm.
it there's n points here and n is large, then you're cool. Yeah.
Yeah, I mean, they're all, yeah, it's always presented at once, usually. But
Because
mm,
we got an add operator, right?
right.
So, okay. Yeah, if you did it that way, then we could extend the data structure so that it had two forms. One that was a linked list and more friendly to that, and the other one that was, nope, here's a big block.
Hmm.
So, yeah, cool.
So a big block of they could be just random, right? But
Yeah, then
um,
it would be, we just store the tuple pairs of, you know, point coordinates and the pointer to memory. That would be the minimum. You could try to search for adjoining ones and pack it down more, but you're making the data structure more complicated.
yeah, yeah, because then you'd have to, then you're kind of, yeah,
And you have to say, well, this is a run of 3 starting here, and here's the pointer or pointers, yeah, you could do it.
yeah. And I think the derived type getting created for a hyperslab is much different than, I don't even think it's using different mechanism for the point selection, I believe, and at NPIO layer.
Uh, well, I mean, we tried to present everything to MPI and go, here you go. It's a matter of how good the query optimizer, so to speak, in MPI is.
Right. Yeah. But it's yeah, it's still a very common use case. So
Mhm.
yeah, maybe that's
Any idea how close to the speed of light this 20-ish second number is?
what?
I mean, is that like limit for the disk or the file system in this case,
Well, I
or
didn't time the writes, but yeah, I don't. I yeah, I did, this is just the whole code because I wanted to include the open, the creation, the writing, and then the closing of a just to make sure that I included everything. But yeah, I didn't time just the writing.
yeah, it would be interesting to know in that, compare that to like raw bandwidth of the underlying file system.
Mm-hmm.
Because if we're off by a factor of 10, then wow, there's a lot of room for all kinds of improvements. But if it's just a few percent, then well, why bother with this extra data structure?
Yeah. Yeah. Okay, that's all I have to share today. Last minute questions, I guess, for wrap up. Okay, Lori, do you talk about the next call of the doctor?
Sure, yeah, next one, it will be Garrett, so that's one of the 5th Tuesdays of the month, so Garrett will be taking a turn next week. Thanks everyone for coming, thanks Scott for presenting.
Okay, bye.
Thank you.
Bye.
Al.